As you might imagine, in chemistry, we really want to be able to predict what's going to happen when we mix substances together. If we are going to get a reaction, and if so, what products are going to be yielded from that reaction. Now, a very handy tool to make these kind of predictions is the concept of acids and bases. And essentially, it was noticed that if you had a shelf and you had carefully selected the substances on the shelf, so let's say we have this shelf over here, and we had another shelf with some carefully selected substances, you could choose any one of the substances in this shelf, and you could also choose any one of the substances in this shelf, and you would be guaranteed a reaction between them. And you might even know something about the products of that reaction. So that's the concept of acids and bases. Just a very handy categorization. We know that something that's an acid is going to react with anything from the bases shelf, and something that's a base is going to react with anything from the acid shelf. And there's some underlying mechanism that ties them together and causes them to react. Now, acids, they tend to be sour, they're capable of dissolving metals. Bases, they tend to be more bitter, they feel slippery in your hand because they're dissolving the proteins in your skin. Use them to make soaps and things like that. And that's just kind of an arbitrary division, though. But what matters is that we have this box and we have this box. Now there are some different ways of defining these boxes here because we can have different mechanisms of reaction. Now you're probably familiar with the Arrhenius definition. If you've encountered acids and bases before, this is usually the first one that's introduced because it's the simplest. An Arrhenius acid is going to be something that forms H+, so that's a proton, it's a hydrogen, it's lost an electron, in aqueous solution. So we'll have our hydrogen and some conjugate anion, and when we put it in water, it will dissociate into the hydrogen ion and whatever the other negative ion is. Example of that, we have nitric acid. We add it to water, then we'll get our H+, and we'll get our nitrate ions in the solution. An Arrhenius base is going to be something which forms OH- hydroxide in aqueous solutions. So when we add it, we'll get some positive cation, which was formerly paired with OH-, something like barium hydroxide. We get our Ba2+ and our OH- here. And I should go ahead and balance this. We actually have two of those. We also said that we would get a reaction between these substances. So this is the general Arrhenius reaction. We call it a neutralization reaction because we neutralize any acid that's present by adding base to it, or any base that's present by adding acid to it. So the H+ that we generated and the OH- that we generated will react to form H2O, and then the remaining ions will pair together. And that's the general form of an Arrhenius neutralization reaction. So if we have sulfuric acid, this will produce H+ in solution, and potassium hydroxide, this will produce OH- in solution. Then we will get water. In balancing this, we get two waters because we had these two H's that are going to come from the H2SO4. So then we doubled the number of KOH's here. And then we will get K2SO4 as our remaining substance. Now, there is an issue that we run into as we start to do more and more chemical reactions. We start to run into some interesting compounds like ammonia, NH3. And the reason that this is interesting is because ammonia, if we add it to water, will do something very similar to what an Arrhenius base does. It will increase the OH- concentration of the water. And it does so through this reaction. So it reacts with the H2O, produces the OH-, And we also get this substance, ammonium, NH4+. Well, that's very similar to an Arrhenius base, but ammonia is not an Arrhenius base. It doesn't contain any hydroxides in it that it releases into water. Well, ammonia also reacts with Arrhenius acids. So if we take our ammonia and we add some hydrochloric acid, then these substances will combine together and give us ammonium chloride. Okay, so this behaves suspiciously like a base, but for some reason, by our Arrhenius definition, it's not included. So now we have two groups of substances that we can pair off with these Arrhenius acids. What can we do about that? It'd be kind of nice if we had one collective definition that would apply to all of these. I'll enter the Bronsted-Lowry definition. This is the most widely used definition of acids and bases in chemistry. And this is going to broaden our category of bases to include things like ammonia. Now, by the Bronsted-Lowry definition, an acid is now going to be something which donates a proton, gives hydrogen to some other substance. And a Bronsted-Lowry base is going to be a substance which accepts that proton, that H+. So this will be the reaction that we have. We have ammonia reacting with water. So here, the water is going to give up one of its protons and become OH-. And since it gives a proton, according to the Bronsted-Lowry definition, that makes it an acid. Ammonia is going to accept that proton and become NH4+. So that makes it a base, according to the Bronsted-Lowry definition. Now, since it's an equilibrium reaction, it can also go in reverse. And so this NH4+, which is the ammonia plus a proton, well, it can go this way and give back that proton. Well, something that gives back a proton is an acid. And here, we have formed this hydroxide, but it can go ahead and take back the proton that it gave away when it was water. Well, a substance which accepts a proton is a base. So these are going to be called conjugates just to distinguish them between the left side. So here we have, if we run the reaction the opposite way, this behaves as an acid, this behaves as a base, and so this will be the conjugate acid to our base on this side, and this will be the conjugate base to our acid on this side. So that's the general form of a Bronsted-Lowry neutralization reaction. We have some acid and base on the left side, and they're going to produce some conjugate acid and base on the right side. And of course, we can flip this, and then we just call these substances the conjugates and these other substances the normal acids and bases. Let's look at writing a Bronsted-Lowry reaction. We'll consider an acid and a base. So we'll consider chlorous acid, and we'll consider cyanide ion. So first of all, start with the chlorous acid. This is an Arrhenius acid. It's an ionic compound made up of the chlorite ion and then hydrogen. So it can dissociate into the hydrogen and the chlorite. Now when it reacts with water, we're going to have water accept this proton given by our acid, and so it will become H3O+ when it accepts that proton. And then the HClO2, giving away the proton, now becomes the chlorite, the Cl2O-. Now, of course, we reverse this reaction. Cl2- will then be accepting this proton back. And so since it accepts the proton, that makes it the conjugate base. Since this would be giving away the proton, if we go that direction, that makes that the conjugate acid. Now, if we consider our cyanide ion, This obviously can't give a proton, but it can accept a proton. In fact, it would like to. It has, a -1 charge, so if it accepts an H+, then it can become neutral. So it's going to act as the base in this case, accepting a proton from water to become HCN. And since water gave away a proton, it will become OH-, our hydroxide. Now note something interesting here. In our first reaction, we had water behave as a base. In our second reaction, we had water behave as an acid. So water is what's called an amphoteric substance. That means it can function as either an acid or a base. In fact, water can react with itself. This is called the autoionization of water. So a water molecule can react with another water molecule. One will behave as an acid and give away a proton to become OH-, and one will behave as a base, accepting that proton to become H3O+. Regrettably, we may find ourselves in the same pickle we were with the Arrhenius acids and bases, which is that even with our Bronsted-Lowry definition, sometimes we encounter substances which seem to behave like an acid or a base, but don't quite fit our definition. If you consider the reaction of our fluoride with water, in that case, this fluoride behaves as a base, and so it will accept a proton from the water to become HF and produce hydroxide in the solution. Well, our fluoride can also react with things like SiF4, and in this case it produces SiF6 2-. So is this still behaving as a base? Is this an acid in this reaction? Turns out we can conceive of it that way by broadening our concept of acid and base by the Lewis definition. So this will significantly broaden what we can consider an acid. It also adds a few new cases to what we consider bases, but for the most part, these are going to be our Bronsted-Lowry bases. So a Lewis acid is going to be defined to be a substance which accepts a pair of electrons. Now, in order to accept those electrons, it has to have an available orbital to stick them in. So that's your hint here, is look for something that has available orbitals in it. And there could be any number of reasons it has an available orbital. Being short in an octet is a pretty good one. A Lewis base then is going to be the substance which donates that pair of electrons. So now we have our mechanism is going to be to transferring the electrons. So that's what's going to connect our acids and our bases. And the Lewis neutralization reaction will be our acid combining with our base is going to produce some new molecule. And this is either called an adduct, or it's also referred to as an acid-base complex. Okay, well, let's look at a reaction where we have ammonia react with boron trifluoride to produce this ammonium boron trifluoride. If we draw the Lewis structures for these, then ammonia here has this pair of electrons available that it can donate. Boron, you may note here, does not have a full octet. It has 1, 2, 3, 4, 5, 6 electrons, it's shy of 8, and so it can fill its octet if this ammonia is kind enough to share these. So we form a bond between these. Now that makes this the acid. It accepts the electrons. That makes this the base, since it donates the electrons. And this is our Lewis adduct, or we can also call it the acid-base complex. Let's look at another example where we have aluminum 3+ combined with water. And we get something kind of crazy here. Aluminum complexes with 6 water molecules Water molecules, they don't have any charge, so we're still going to have that +3 charge that we started off with. So what's going on here? Well, first of all, we've removed some electrons from the aluminum, so it seems like it should have some orbitals available to stick electrons in. Now, clearly we are sharing in more pairs of electrons than those 3 which went missing. Aluminum is also a large atom which can expand its octet to accommodate more than just 8 electrons. So we have our water for our 2 pairs of electrons that it can donate. And we have our aluminum with some empty orbitals. And we get this weird complex with 6 water molecules, all associated with the aluminum. Now, since this was the supplier of those pairs of electrons, that makes it the Lewis base. And since our aluminum was the one which accepted them, that makes it the Lewis acid. Some more guidance on determining Lewis acids and bases. Lewis bases are the easiest. In principle, any molecule that has a lone pair of electrons on it can act as a Lewis base. So look for that lone pair of electrons when you do the Lewis structure. For the Lewis acids, we've seen that with something like boron trifluoride, where we have an incomplete octet on the boron atom, that's a pretty good candidate for being able to accept a pair of electrons to fill that octet. It's also the case if we have atoms with double or triple bonds that we can have these act as Lewis acids. Now, if you consider one of the resonance structures where some of the electrons from our double bond gets moved back over to the oxygen, for example, well, now carbon has an incomplete octet, just like our boron did. So that makes it possible for this to accept some electrons from our Lewis base. And if we have a large central atom, then it might not need to do something like this in order to make room for extra electrons. It might just be able to accommodate more than 8 electrons by default. So that's especially going to be true for as you go down the periodic table and get larger atoms. So something like these compounds, we saw that with the silicon tetrafluoride and the aluminum. These are able to accommodate extra electrons.